Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to start a new part of this course, the final part. If you recall, this course is composed of 3 parts and we've already covered 2 parts. The first part dealt with the science and art of network performance evaluation, and the second part dealt with conducting empirical network performance evaluation. The final part of this course deals with modeling and simulation-based network performance evaluation. And before we get to the core concepts of this part, we need to first of all talk over the preliminaries. And regarding that, the understanding of probability and stochastic processes is very fundamental and very useful for the study that we'll be doing here. So today's session would be a gentle introduction to stochastic processes, and in a way we are going to refresh the concepts that you must have taken and understood earlier in your probability and stochastic course. So why do we need to study stochastic processes? So this is a fundamental question, and this stems from the inherent randomness in the world around us. And also, apart from the inherent randomness, we are always not completely aware of all the details. Every measurement that we can make would be having some error. And the combination of this randomness and error makes this world a very uncertain place. So earlier in this course, we talked of the mathematical formalism of a random variable, which helps us get our arms around a random experiment. So we talked about a random experiment whose outcome is not certain, but we can talk about its long-run behavior. And that is the beauty of probability theory, that random events, while they are random in the short run, they display statistical regularities in the long run. And we want to exploit this so that we make informed decisions and we make better decisions, rather than just be in a way give up because we cannot know the random variable's output in the short term. We should exploit the regularity that appears in the long run. Up till now, we have talked about random variables which talk about assigning probabilities to the outcome of a single event. But in the life around us, everything is dynamic. So you would have often processes that evolve in time. So these are called temporal processes. And we also, just like we addressed the problem of predicting in the long run from a single experiment, we also want to exploit the statistical regularities in these empirical temporal processes that are random, but which have some interdependence, and we can characterize them in the long run. So that is the general idea of stochastic process and a very high-level introduction, and we are going to talk about this in more detail today. So let me now outline the contents of this session. Initially, I'm going to talk about what exactly is a stochastic process. I've already given you the intuition. The study of stochastic process is the dynamic side of probability theory, in which we study processes that evolve in time. Secondly, in this session, we're going to talk about classification of stochastic processes so that we understand what different kinds of stochastic processes exist. And lastly, we're going to talk about representation of stochastic processes. And we would see that there are multiple ways of representing the same process, because stochastic process is essentially like all the other models, and they're only approximations. So for even representing the same system, we can make different stochastic models of that. And accordingly, we would have different representations. The same system, but we can analyze it differently and construct different stochastic processes for it. But initially, we're going to talk about what exactly is a stochastic process. To understand stochastic processes, we should compare it with deterministic processes. And to understand that, let us recall that we've already covered in this course the concept of determinism, the worldview that many scientists had in the earlier 20th century and before that. And that was that given the entire information about the current state of the world, we can predict the next state of the world exactly. So this was from the optimism of numerous breakthroughs and the fast pace of progress in scientific inquiry. And many great scientists believed in this deterministic view of the nature and the world around us. But thereafter, as more precise instruments were discovered, and the excuse that the results do not match with the theory because our information is not correct enough was weakened. And thereafter, we now have a worldview in which we have a statistical viewpoint about the world around us, which is that we cannot know the future for certain, even if we are given all the information about the current state. And if that is the case, and it must be obvious that it is almost impossible to have the complete state of the world available to you. Even if that is available, we cannot predict deterministically that exactly what will happen. The statistical point of view is that you can talk about averages. You can talk in probabilistic terms, and you can say that mostly, this will happen. The chances of that happening is less. The chance of that happening is very less. But you cannot give exact answers. And that is the idea that we exploit in probability. When we have such statistical processes in which we cannot know the outcome of an experiment for certain, the next best thing that we can do is that we can think of all the possible outcomes of an experiment and then attach probabilities to it. And that is the most useful way of dealing with such statistical experiments. So to understand deterministic process versus stochastic process, imagine that we have a person who is standing on a staircase and he jumps one step up at every time tick. And so this is deterministic. We already know the time this person is going to make the jump and also to what state the jump would be. So in such a case, we are exactly aware of how this dynamic process would unfold. So for example, we can say at time is equal to 0, this person is at the base of the staircase, which we call, let's say, state 0. At time 1, he would be at state 1, which is the next higher stair. And eventually, we can predict where this person would be for any time in the future. This is because the way this process is unfolding in time is completely deterministic. In contrast, if we just change the rules just a little bit and we say that, okay, this person is going to jump at every time instance, and that is defined, but the amount of jump he is going to make, or we can even make things simpler, we still say that this person can only go up one stair or he can go down one stair, but he tosses a coin to decide. So when he is at the base of the staircase, obviously he cannot go down. So from there, it is deterministic that, if we have to make a transition and the transition to the same state is not allowed, then he would have to go up. So let's say we have this condition in our example, but when he is at state 1, he would go to the upper stair with probability P and would come down with the probability 1 minus P. If we just tweak this game by just this little amount of detail, this game is no longer deterministic, in the sense that the way this process would unfold in time cannot be predicted. So, for example, if it is asked that where would this person be at time is equal to 10, then we cannot say for certain where he would be. And here is the important point. But still, we can attach some expectation. And that is where the study of stochastic processes comes in. For example, if the rules of transitions are known, we know that some possibilities are not going to take place at all. So we give them a probability of 0. For example, if this person jumps up or down with some probabilities and there are only 10 time ticks or 20 time ticks or whatever, in the case of 10 time ticks, this person cannot be higher than, let's say, 15, the stair having number 15, because he cannot simply reach there even if all possible coin flips come in his favor, which gets him up and up. But even if there are 10 such coin flips, still he will not be able to get to state 15. Also, considering the states which are possible, all of them are not going to be equally likely. And because of that, we can give them probabilities, and we can talk in probabilistic terms. In such a stochastic process, we can also talk of, the question that, okay, this person is at state 0 currently. After 3 transitions, where would he be? So again, we can use the concept of stochastic processes and the tools of probability to help us give expectations to different states. So this, I hope, highlights the difference between a deterministic process and a stochastic process, and how a stochastic process is a dynamic probabilistic process. So in this case, there is a concept of the state of this person being indexed by time. So now there is not only a single random variable, but we would have many random variables. And in fact, this is one of the way we define stochastic processes, that this is a mathematical model in which we have a family of indexed random variables. So there is not a single random variable, but there are multiple random variables that are related to each other. In general, they may be related to each other, and also there is a strict sense of order. So these are indexed random variables. So to understand this in more depth, first of all, let us refresh the concept of a random variable. And we've already talked about a random variable being a number on the real number line, which actually is mapped from the events of a random experiment. So a random experiment can result in many different outputs, and we do not know which outcome would come before we perform the random experiment. But even before we've conducted the random experiment, we have some expectation according to the long-term probabilities. And because of that, we can say that, okay, there can be 3 possible outcomes, and the probability of outcome 1 is, let's say, 0.5. The probability of outcome 2 and 3 are 0.25 each. So overall, something is going to happen, and therefore the sum of probabilities of all possible outcome is 1. But we do not know before we've conducted the random experiment what particular outcome would come. And the concept of random variable is that we do not talk with these events, but we give them some number by mapping the possible outcomes to the real number line. And then once we have this random variable, we can transform it, we can create more random variables from this, and this helps us answer many important questions about the outcome of this random experiment. So to give an example, we can think the example of rolling a die, and on a die we have 6 faces. So accordingly, the face which would come up would be the outcome of this experiment of rolling a die. So this can be either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So we have 6 possible outcomes. In this case, we are going to map these possible outcomes to the real number line in a natural way. If we get one face up, we would map it to number 1 on the real number line. If we have the face 2 up, this would correspond to a random variable value of 2, and so on for all the other possible outcomes. But just this mapping is not enough to act as a complete model of our expectation about this random experiment. In fact, we need something else, and that something else is our expectation about the probability of the random variable taking one of these values. And this is represented by a probability mass function in the case where there are discrete number of values that the random variable can take. And in such a case, we would call this a discrete random variable. In general, a random variable can also take a value within an interval, and then it would be called a continuous random variable. And to define the probability then for all the points, we make use of probability density function. And this is because the probability of the random variable taking any particular value is 0, because there are infinite number of points between 2 points on the real number line. But we can talk about the continuous random variable taking a value within a certain interval. This may be very small, in an infinitesimal small interval, and then we can talk about probability density function, which tells us the probability that the continuous random variable would be in this range. So we will come to the probability mass function and the probability density function. Let us now analyze this experiment. So for this, we see that for each of the outcome, and there are 6 outcomes, we have equal probability. And accordingly, because the total probability has to sum up to 1, every outcome has a probability of 1 by 6. And there are no other probabilities. The random variable would take a value of 1, 2, 3, 4, 5 or 6. It cannot take any other value. So this is again how a discrete random variable works. It can only take a value from discrete number of possible values. And these discrete number of values may be finite, as in this case, because we only have 6 possible outcomes. We can also have the case where the outcome of a discrete random variable is infinite. But then this has to be countably infinite. If you recall from your course on probability and stochastic processes, a countably infinite set is a set that can be put into one-to-one correspondence with the natural number. And an example of a countably infinite set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this series going on forever. So this is infinite because whatever the largest number we can think of, this series will go beyond that. But still, we can count the states that we have, and because of that, this is called countably infinite. So it must be stressed that for a discrete random variable, it's not necessary that the outcomes be finite. We can also have infinite outcomes, but these infinite outcomes must be countable. So the question is now, how do we assign the probabilities? And this has a philosophical answer. And usually in the textbooks, we're given the frequentist approach, in which we say that, okay, what is the probability of a coin coming heads up or tails up? We say that if we do this experiment infinitely long, and then we check the proportions, this will tell us the probability of a heads and a probability of a tails. So while this works in mathematics, in life, in the long run, everyone is dead. So there are no infinities in real life. So the question still remains, how do we conduct an experiment infinitely long? Also, there are questions which cannot be done infinitely long. So for example, you want to see before you get married, what are your chances of having a successful marriage? You cannot, even if you want, have infinite number of marriages. So this is a one-off event in most cases, and on the basis of this, we do not have the luxury of thinking about infinite experiments. And for such cases, subjective probabilities have been devised. And there is a lot of detail in this, and much of it has to deal with the philosophy of probability. But it must be understood that there are different ways of assigning probability, and then we can use the approach of probability theory to manipulate these probabilities to get some useful answers. So with that said, now let's talk about some specific kind of random variables. And I would advise you now to go back to our earlier lectures on common distributions, because when we talked of a distribution earlier, it was the distribution of a random variable. So let me repeat. A random variable will not take a deterministic value. It can take a range of values, and we call that range a distribution. And all the individual points in this distribution are not equally likely. Some are going to be more likely than the others, and that is defined by the probability distribution functions, the density function and the mass function that we have covered earlier in our lectures on common distributions, where we covered continuous distributions as well as discrete distributions. But I'm going to just refresh the concepts just a little, so that even if the things are forgotten, we refresh the most salient points so that we can move ahead. In a discrete random variable, as mentioned earlier, the outcome of this experiment can only take a discrete value. It may be finite, it can also be infinite, but it has to be countably infinite to be in the discrete class. So as examples of discrete random variables, we can consider a binomial random variable. And in a binomial random variable, we're interested in conducting experiments, and then we are interested in seeing that how many successes were there in these independent experiments. So I would advise you to go and see the details in the earlier lecture on common distributions. Apart from a binomial random variable, we also have other discrete random variables that are very commonly used. And a random variable distribution which is very commonly used in network performance evaluation is the Poisson distribution. And this can be thought of as the limiting case of binomial random variable. In a binomial random variable, we conduct, let's say, n number of independent experiments, which can be thought of as simple coin tosses. So you can only have two possible answers, and then we are interested in seeing of these two possible answers, in which we would call one arbitrarily a success and the other failure. And if we do this enough number of times, we are interested at the end that how many successes we had. In a Poisson random variable, we think of this in the form of very fast coin tossing, in that we are conducting a coin toss in every infinitesimal small interval. And accordingly, this would be the limiting form of the binomial random variable. And the probability mass function of this is given on the slide now. Let me now define more precisely what is the probability mass function. This is defined as the random variable taking that exact value. So if I say that PMF of this point is this, then we say that the probability of that random variable taking this exact value is this. And the notation for this is, sometimes there are many different notations for this. One way of representing this is as a small p with a subscript of capital X, and within brackets we have the small x. And we say that this is the PMF of this particular value, and that essentially tells us the probability of the random variable capital X taking the value small x. We also use the notation P of X and also F of X to sometimes refer to the probability mass function of X. So we must be aware that there is a lot of diversity, and different authors sometimes use different notations. So from the context and hopefully the knowledge gained from this and other courses, you'd be able to make out what is being referred. Okay, let's now talk about a continuous random variable. A continuous random variable takes a value from a continuum. So you have an interval, and any possible value from that interval can be chosen. So examples of continuous random variables are many, and we've seen many already. So the normal distribution is a continuous random variable. The exponential distribution, it's a very important distribution and intimately tied to the Poisson distribution. It is also a continuous random variable. A Poisson distribution is not a continuous random variable. It is a discrete random variable, but the exponential distribution, which is very closely tied with Poisson distribution, and it is essentially a way of looking at the same system with a different viewpoint. The exponential distribution is continuous time. And then we talked about various generalizations of the exponential distribution, the gamma distribution, the Erlang distribution, the Weibull distribution. We also have the log normal distribution, the wild randomness kind of a continuous random variable, the Pareto distribution. All of them are continuous random variables. So they give us a value from a continuum or an interval. Any possible value can be chosen. So to define it more precisely, we say that in a continuous random variable, the possible outcomes are uncountably infinite. So this is in contrast to the discrete random variable, where the outcomes have to be countably infinite. Here we can have uncountably infinite value taken. And I would like you to go back and read and listen to the discussion about George Cantor and how he discovered the concept of infinity. We talked about that briefly in our lectures on fractals. Okay, so how do we actually describe a continuous random variable? Because the difficulty now is that this random variable can take infinite number of values, because it can take any value from a continuum, an interval. And accordingly, the probability of any single point is 0. So we cannot use the concept of a probability mass function, which we define for a discrete random variable, and we cannot port it directly to a continuous random variable. Instead, we can talk about this in two different ways. We can talk about the probability that the random variable would take a value which is equal or less than this. So this is the idea of a cumulative distribution function, and this is the preferred way of dealing with continuous random variables. And then the derivative of this is the probability density function. And if you see the slide now, you may recall our discussion on this when we talked of common distributions, that the probability of any single value is 0, but we can talk about the continuous random variable taking a value in a range. So if we talk of CDF of 0.1, approximately 0.1 as highlighted now on your slide, what is the probability that the continuous random variable would take a value which is either equal to this or less than this is defined by the cumulative distribution function. And the formula of that is written on the slide. The important point is, when we differentiate this and we get the probability density function, that density function is not highlighting the probability of the continuous random variable taking exactly precisely that value. We've already mentioned that the probability of taking an exact value is 0. It tells us in a limiting sense that if we construct a very small infinitesimal interval around it, this is the probability that we would have. So there are two alternative ways of dealing with a continuous random variable. We've talked of the cumulative distribution function, and we've talked of the probability density function. Let's now see the notation used for this, because this is again a source of confusion. Because if you read different books, the authors typically use sometimes different notations to refer to the same thing. But it's fairly standard to refer to the cumulative distribution function with a capital F. And if we are referring to the probability density function, we use the function in which we have the small f. So if you note, I've already stated that the probability mass function is also expressed by the same notation of f of x, but then the context would tell us that if this is a probability mass function or a density function. A very important continuous random variable is the exponential distribution, and it helps us to model empirically observed times between successive arrivals. So let's say you are in a shop and you want to time the inter-arrival time between the next two arrivals. So in that case, the inter-arrival time, we can model it by exponential distribution. Exponential distribution is a very interesting distribution, since this is a memoryless distribution, in which case the intuition is that if you have waited for some amount of time, your expectation of how long would you still have to wait would remain unchanged. So having this information that you waited for this amount of time does not change your expectation at all. So I've already mentioned that exponential distribution is intimately tied with the Poisson distribution. And I've talked that we can, informally speaking, think of a Poisson distribution as very fast coin tossing, in which in every infinitesimally small interval, we're doing a coin toss in which we can have a success or a failure. When we talk of the exponential distribution, this is the continuous counterpart of the geometric distribution. And we can think of this in the terms of how many coin tosses would it take before we get the first success. So including the success, that would be the time it takes. So now it would make sense that why we say that exponential distribution is a memoryless distribution. Because since the coin tossing in every infinitesimally small interval is independent, so whatever has happened before does not affect the future. So accordingly, if you have waited for some amount of time, the expectation for you, the mean that you expect to wait, would still remain the same. And this is very important, and because of that, I have tried to make it clear by reiterating this point multiple times. In an exponential random variable, the mean and the standard deviation is the same, and it is equal to 1 over lambda, where lambda is the rate of the equivalent Poisson process. We've seen earlier in the lectures on common distribution that exponential distribution is a distribution with mild randomness. So given lambda, we would expect that most of the arrivals would be around this. So it's not like a Pareto distribution, it's not a long tail distribution. So mostly the values would be close to the mean, and accordingly the standard deviation is the same as the mean. The probability of waiting a time capital T, where capital T is somewhere between t and t plus dt, is given as lambda exponential minus lambda t multiplied by dt. And this is because we cannot specify the probability of one particular time, but we can talk about the probability in an infinitesimally small interval, which is expressed here by dt. Okay, let's now proceed forward and talk about expectation of a random variable. And this is where probability gets useful for us. In many practical domains where the outcome of something is random, we still do not expect that everything is going to be equally likely. We expect that the outcomes would have some distribution. And if we have information about that distribution, about the possible outcomes of this experiment, we can then attach our expectation. And the idea of expectation, the terminology expectation, formalizes this intuition. And it is expressed in a very simple manner. If capital X is discrete, in other words, if we have a discrete random variable, it's just the summation of the value multiplied by the probability of the discrete random variable taking that value. And if you sum it up over all x, so we would have the expected value of capital X, the discrete random variable. In a continuous case, we replace the summation with an integral, and accordingly we calculate the expected value. So it must be stressed here that this expectation uses the probabilistic law of large numbers, in which the statistical regularity of a process or a random variable manifests itself in the long run. Accordingly, we expect that if we were to repeat this random experiment multiple times, infinitely long, then this would be the mean value that we would have. So in that sense, we can call expectation as a kind of an average, but this average is a probabilistically weighted average. Also, if you recall our discussion on logical fallacies, we mentioned of a sarcastically named so-called law, which was the law of small numbers, which is a fallacy which people have. So they would think that the expectation is 3.5, so we would have this as the average in the short run as well. For small samples, we would have the same thing happening. This is not always the case, and we should expect the average to show itself in relatively large number of samples. In this case, the expectation is 3.5, but we will never have the roll of a die coming up as 3.5. So this is like the example we saw of an average gone wrong, where we said that we think of the family with an average size of 2.4 children. This thing is not going to be ever the case in a single family. But if you think of a very large population, then averaging over all of them, we get this abstraction. This is an abstraction which helps us reason about this population, but because this is an abstraction, this does not give us the detail about every single family. So we must remember this, that averaging also loses a lot of information, and it's just a model, and models are useful, but when they are used outside their domain, they may lead to errors. We've talked about random variables now, both of the discrete kind and of the continuous kind. Now it's time to progress to stochastic processes, and we have defined it as a family of indexed random variables, where these random variables may also be dependent on each other, and also they have a sense of order. So you have a random variable for this time instant, and you have a random variable for a following time instant. And the following time instant's random variable may be dependent on the random variable that we have here. So accordingly, stochastic processes are a little more complex than simple probabilistic random variables, which deal with just a single random experiment. We can classify the stochastic processes into two broad categories according to the way we index them. So this is, in a sense, when are we observing this process? So if we have a continuous time stochastic process, it may be that this stochastic process may change state at any given time. So in that case, because it can change state at any possible value in a continuous range, we call this a continuous time stochastic process. And there are multiple examples of this. A Poisson process is a continuous time stochastic process, since it counts the number of events happening in some interval. And because these events can happen at any given time, we do not call this a discrete time process. This is a continuous time stochastic process. And Poisson processes are used a lot in queuing theory. In fact, all of the elementary queuing theory assumes Poisson processes and exponential distributions because they are simple to deal with, and in this case, relevant to our discussion, they are continuous because the event can happen at any given time. There are many examples of usage of stochastic processes in finance, in physics, and in fact I can go on, but I'll give you an example from physics, and that is the observation of Brownian motion, which was first of all discovered by Robert Brown, who was a botanist, but thereafter it was used, the erratic and haphazard movement of pollen when suspended in water was also studied by Einstein, who then used it to provide many results about his atomic theory. So the motion of pollen grain when suspended in water is random. So if we are interested in estimating the possible trajectory that this may take, then we cannot talk in deterministic fashion. We can only talk in terms of probability. And this is the beauty of probability theory. Even at the most fundamental levels of understanding the nature, quantum theory tells us that even the path taken by a molecule in some gas is undeterministic. We cannot trace the path of any single molecule, but then we can talk in terms of average energy. We can talk about the average over a lot of molecules. And when we know that, we can construct pipelines to transport such gas across continents to a city of millions. And this is because we can use something even if we do not know that in a deterministic fashion. Stochastic information or probabilistic information is good enough for many useful tasks, and that is essentially what engineering is about. So we've talked about Poisson process as a continuous time stochastic process, and it can be used to model the number of customers in a waiting line. Okay, let's now talk about a discrete time stochastic process. So as an example, let's say we want to trace the trajectory of the weather across time. In other words, we want to observe the temperature in Lahore every day in the morning, and we want to do this repeatedly every day. And we do this for a period of time. So this is a stochastic process. And you can see that there is some dependence as well. So if you have some random variable to represent the temperature now, the next day's weather and accordingly the random variable associated would be dependent on each other, because it would be rare for a very hot day to be followed by a very cold day, and vice versa. So these random variables are often dependent on each other. And if you see the slide now, you would observe that we have two lines shown, and one is the high temperature, the other one is the low temperature. And this is a stochastic process because we cannot predict in a deterministic fashion what would be the weather 90 days from now. In fact, most weather prediction is very short time based, because weather prediction is chaotic. Initial conditions make a large change. So for studying such processes, we often make use of two kinds of averages. One kind of an average which must be familiar is the time average. So if you observe the red and blue lines, each one of them is a time series. And this is just one possible sample from the stochastic generative model which we can imagine is creating the weather. So from that we can have many possible sample functions. So if we consider just a single sample function as is shown on the slide here, we considering the time average. We consider a single function and we consider it over a period of time. This is the time average. But if we have a fixed date and we think of now what possible weathers we could have on this date, then all the possible states would be the ensemble, and then we can talk of an ensemble average here. Okay, now let's move on, and up till now we have classified stochastic process as continuous time and discrete time, but we will see that there are other ways of classifying stochastic processes, and two of the main ways that we can characterize, apart from the index parameter, which we've seen the time parameter may be continuous or discrete, two other main classification bases is that if the state that the process can assume is continuous or discrete, and also what kind of dependence the random variables have with each other. Since stochastic process is a family of random variables, we want to know what kind of dependence they have. So today and in this session, we are going to talk about, we've already talked about the classification according to the time index. Now we will be talking about the classification according to the state space. What possible states can the process adopt? In the coming session, we're going to talk about stochastic processes and how they may be classified according to the dependence between the random variables. So now this is straightforward. We have two kinds of classes according to the time parameter. We would also have two kinds of classes according to the state parameter. So all in all, according to these two basis of classification, we would have four kinds of processes. The first one is the discrete time, discrete state stochastic process. So if we consider and go back to the earlier example, this would be the person jumping up and down on the time tick, and this is a fixed time tick. Every time tick we have to make a transition. And if you observe, the possible stair he would be at is countable. It may be infinite if we think of an infinite staircase, but it is discrete. Accordingly, it is a discrete time process and a discrete state process. Example of such a process would be a Bernoulli random process, in which at different discrete times we would be conducting a random experiment which can result in a 0 or a 1, two possible outcomes. And if we have a random variable for each possible time instance, then this is a Bernoulli random process, which is a discrete time, discrete state stochastic process. We can have a discrete time continuous state process. So in the example, this would be a person sliding up or down on a ramp. So now the ramp is continuous. There are no states. It represents a continuous range of values. So accordingly, we are forced still to make the transition on discrete time ticks, but the state can be continuous. An example of this is a Gaussian random process that is sampled in time. The state can be continuous, but the observations are discrete. The other class is continuous time discrete state stochastic process, in which we can make the jump at any given time, but the state is discrete. In the example of the staircase, the number of stairs are discrete. It may be finite or countably infinite, but it is still discrete. As an example of a continuous time discrete valued process, we can think of a Poisson random process, which is a counting process in which we are counting that up till this time, how many events have taken place. The figure that is shown is the binomial random process, and this is just considering the first process that we saw of the Bernoulli process. If we are conducting these Bernoulli trials on discrete times, and if we count the number of successes, this would be a binomial random process. This is continuous time and discrete state. Okay, let's now talk about the final of the set of 4 classes, the continuous time and continuous state stochastic process. I'm sure now you'd be able to guess the pattern. The person can move at any given time and he can slide up or down by any number. So, and this number is not discrete. Example of such a process which is continuous time and continuous state is the Gaussian random process. Okay, now I'm going to talk about representing stochastic process very briefly, and I'm going to say that stochastic processes can be represented in multiple ways. For example, if you see on the slide now, you can see that the left graph tells us the number of people in queue versus time. So this is a stochastic process tracing the number of people in the queue. The other way of looking at this is to look at the arrival process, which tells us that up till this time, how many arrivals have taken place. Also shows the departure process, that up till this time, how many departures have taken place. In fact, using the second graph, we can construct the first graph. And that is the point I'm trying to make. For the same system, you may model it in different ways. I'm going to now very briefly talk about the main ways of modeling a Poisson process, which is a process which tracks the number of events in some time. We may model this as an arrival process in which we are basically calculating the time instances at which we had arrivals. So for example, the first arrival came at S1 time, the second arrival came at S2 time, and the third arrival came at S3 time. So we have a discrete time in the sense that we are making discrete observations, and the state in this case would be continuous, and it would be for the first index it would be S1, for the second it would be S2, for the third it would be S3. The point that you must understand here, that this arrival process would be non-stationary, because it would always keep on increasing. So if we are interested in making the process stationary, well, we can look at the time between successive arrivals, and this is known as the inter-arrival process. If we are actually tracking the inter-arrival time along with our observation points. So the time from the start to S1 would be the first observation, X1. The second observation would be X2. The third observation is X3. It must be clear to you that these are alternative ways of looking at the same thing. And lastly, we can think of this as a counting process in which we are counting the number of events or the number of arrivals that have taken place up till some time. So everything that has happened before would be counted. And a Poisson process is a counting process. And in the next session, we're going to see a generalization of Poisson process known as renewal process, which is also a count process. Let me now wrap up this lecture by highlighting the salient points I've covered today. I've talked about stochastic process as a family of ordered random variables which we can use to model empirical process that is evolving in time. And we have also talked about how it is very important for all the analytical methods, and accordingly we're going to develop this further in our next session. So till next time, Assalamu alaikum wa rahmatullah.